So in the previous lecture, we saw that we would like to look at programs as functions that transform inputs to outputs. So a program is basically a set of rules that describes how to produce a given output from an input. And a computation consists of applying these rules and transforming the input to the output by repeatedly rewriting expressions based on the rules given. So the way we write a program is to start with some built-in functions and values, and then we use function composition and things like recursive definitions to build more complex functions from the basic built-in functions and values given to us. So another thing that we need to be aware of when we are dealing with functions is to look at the values that they manipulate. So these are what we call data types or just types. Right? So functions are defined over fixed input and output types. For instance, we saw last time the function successor, which adds 1. Now the successor function that we defined assumes that the inputs are the whole numbers 0, 1, 2, 3, and as output it produces another whole number. We also looked at definitions of plus and multiply. So plus and multiply each took two whole numbers as input and produced a whole number as output. Now notice that if you add two whole numbers or you multiply two whole numbers, you will necessarily get a whole number as an output. Now you could also define similar functions plus and multiply for values that are not whole numbers or even successor. Right? So plus 1 could be defined for any value, but successor means something. Successor means the next number. So it makes sense to say that the next whole number after 1 is 2, but it doesn't make sense to say that the next fractional number after 1.5 is 2.5. Right? There is no next fractional number, which is why successor is usually defined only for whole numbers. But if we think of successor not as successor as plus 1, okay, then we can define plus and multiply the general addition even for fractional numbers. But these will be different functions. So what about a function like square root that takes the square root of a number? So here, notice that even if the input is a whole number, the output need not be. The square root of 4 is 2. Okay? But the square root of 2 is in fact an irrational number, but at the very least it is a fractional number which is neither 1 nor 2. Right? So we have two different types of numbers that we deal with. We deal with these whole numbers or integers, and we deal with numbers which have fractional components. Right? The problem with fractional components is that this value after the decimal point can be arbitrarily long. It could be infinite in general. And so to precisely describe a fractional value requires an infinite amount of information. So now in mathematics, typically you write sets like R for the real numbers and Z for the integers, and you assume implicitly that the integers are those real numbers which have a zero fractional part. Now when we write programs, it turns out that representing integers and representing fractional numbers are very different. And therefore, these are distinct types for us. So we will always differentiate between whole numbers and fractional numbers when we write functional programs, even though mathematically one is often seen as a subset of the other. Now, many interesting programs manipulate values which are not numbers. For instance, when you use a text editor or you enter a URL in a browser, you are typing some text, and then the program, that is the web browser or your text editor, has to interpret this text. Right? So characters are a very important type in programming. So think of a very simple function that we can write, something that takes an input letter, and provided it's a valid letter of the alphabet, not a punctuation mark or a number, it capitalizes it. So capitalize of small a is capital A, capitalize of small b is capital B, and so on. So for such a function, the input and the output consists of characters. So whenever we write functions in a functional programming language, we will have to ensure that the function's type is well defined. In fact, it will turn out that the functional language we are going to use, which is Haskell, will not allow us to write a function whose type is not defined. Now, not defined can mean many things, but one of the things it means is that the output must be uniform. So you cannot have a function which on some values produces an integer as an output and on some other values produces a character as an output. Okay, so this will be the kind of limitation that we will see. So all functions will have to have a well-defined type, and therefore the same function which say mathematically does the same thing like plus which mathematically does the same thing for whole numbers and for fractional numbers, will actually consist of two different functions. Now it may be that for convenience we use a symbol like plus or the name plus to define both functions, but in actually internally they are two different functions because they have different types. So now not only do the inputs and the outputs of functions have types, the functions themselves have types. We will see that we can write functions which take other functions as input and manipulate them. For instance, we can think of a function. Okay, so we saw that, for instance, plus 2 is successor of n. So plus 2 of n is successor. Now in general we could say that why fixed successor? Why not say that we say apply twice and we take as input a function and a number, and we said the output is the result of applying the function twice to n. So here notice that the function itself is being supplied to our new function and it is being used twice in the output. So there is nothing that prevents us from writing functions which actually take other functions as arguments. And now if we assume that all functions must have well-defined types for inputs and outputs, functions must also have types. Now the notion of a function type is not very new to us. In mathematics, if we write a function from a set S to a set T, we write f colon S arrow T. This means inputs come from S. So S is often called the domain of the function f. And outputs are from the set T. So this is often called the codomain. And in particular, the range of the function is that subset of the codomain which is actually reached by values from S. So we have this notion of an input set and an output set. So a type of a function in a programming language is exactly that. It says take the input type and the output type and say it transforms values of type A to values of type B. Okay? So a type is just a set of values. Right? So when we say we have the set of whole numbers, then it just means that the values permitted are 0, 1, 2, 3. We say we have a set of characters, then we have a set of symbols that we are allowed to type. If we have the fractional number, then there are certain values that we can define with decimal points. So a type is just a set of values, and just like in a mathematical notation we write a function from one set to another, we use the same notation to denote the type of a function, and this is important because one function can be actually fed to another function as input, as we will see. The other interesting notion is that of building collections of values. Right? So if we have whole numbers, then we have individual values 0, 1, 2. Now we can have sets of whole numbers, for example, in mathematics. Okay? So a set of whole numbers is a collection of whole numbers, say 1, 3, 7, and we write it with some notation to indicate that this collection, say maybe curly brackets and commas. Okay? So similarly in programming, we often want to deal with collections of values. We might want to talk about a sequence or a list of integers. Or when we type words, then a word consists of a number of characters. So it's a sequence of characters. Or we might talk about points, okay, in space, xy coordinates. So an xy coordinate is just a pair of values like 7.3 and 4.2, right? So we want pairs of numbers. Okay? So if we have types for the components, then we have a type for the whole. So we can say that I have a pair of fractional numbers, I have a sequence of integers, or I have a sequence of characters. Right? So collections are also important types. So a type, remember, is now just a set of permitted values. So it tells you, if I tell you the type, then you can tell me whether a given value is legal for that type or not. If I tell you that the type is whole numbers, and I ask you whether 7.5 is a whole number, you can say it's not a whole number. If I ask you for a list of integers and I ask you the list consists of 1 followed by 2 is a list of integers, you'll say yes, it is a list of integers, and so on. Okay? So to summarize, we are talking about functions that manipulate values, okay? But the values must come from well-specified sets or types. So each input and output value comes from a well-defined set of possible values, and we will only allow function definitions whose type is precisely specified. And given the types of the input and the output, we saw that the function itself will have a type which is from the input type to the output type. And finally, we saw that it is important to have collections of values, so lists of integers or pairs of characters, right? So we want to combine individual values or smaller values into larger values which can store multiple values of the same type.